Hello! In this video, I will present our project entitled Temperature Regulation of a Room. The main objective of this project is to design a system capable of automatically maintaining the temperature of a room around the desired value called the set points. This project is based on two main parts: a simulation using MATLAB Simulink, followed by a real implementation using an Arduino board. The system operates according to an automatic control principle. It measures the ambient temperature using a sensor, compares it to the set point set by the user, and then acts automatically. If the temperature is below the set point, the system activates the heating. If the temperature exceeds the set point, the system activates the ventilation. Before implementing the real system on Arduino, we started with a very important phase: the modeling and simulation on the thermal system using MATLAB and Simulink. These steps allows us to understand the dynamic behavior of the room, to analyze thermal losses, and to compare open-loop control and closed-loop control with a PID controller. The simulation also enables us to validate the controller's performance before the real implementation. The room is modeled as a closed thermal system. It consists of a volume of air represented by a thermal capacitance and walls that cause heat losses to the outside, represented by a thermal resistance. The heat source is an electric heater whose power represents the input of the system. The outdoor temperature is considered as a disturbance. The model is built using Simulink and Simscape thermal blocks. The thermal mass block represents the air contained in the room. It stores thermal energy and determines how the temperature evolved over time. The conductive heat transfer block models the thermal losses through the room walls. The ideal temperature source block represents the outdoor temperature fixed at 0 degrees Celsius. The heat flow source block applies the thermal power supplied by the heater. Finally, the temperature sensor block measures the indoor temperature and sends it to the controller. First, we studied the system in open-loop mode. In open-loop operation, the heating power is applied directly to the system without taking the actual measured temperature into account. Therefore, there is no automatic correction. In this first case, constant power of 500 watts is applied. The curve shows a gradual increase in the room temperature. This indicates that the supplied power is sufficient to compensate for heat losses to the outside. To improve the system's performance, we used closed-loop control. The measured temperature is compared to the set point, which is fixed at 30 degrees Celsius. The resulting error is sent to the PID controller, which automatically adjusts the heating power. The curve displayed on the scope shows a rapid rise in temperature from around 16 degrees up to the set point. A slight overshoot is observed, mainly due to the integral action of the PID controller. After approximately 600 seconds, the temperatures stabilize around 29.8 degrees Celsius. The steady-state error is therefore nearly zero, demonstrating the effectiveness of the PID controller. After validating the system's behavior through simulation, we now move on to the real implementation using Arduino. In this section, we will explain the system wiring in detail. The wiring connects the sensors actuals and display element to the Arduino Mega to ensure temperature measurements compares with the set points and control of the heater and fan. All components are mounted on breadboard and connected to the Arduino using jumper wires. The temperature sensor used in this project is the DHT11. This sensor measures both the ambient temperature and humidity. The DHT11 has three main connections: power, ground, and data outputs. The sensor's data pin is connected to the digital pin 49 on the Arduino Mega. The sensor's power pin is connected to the Arduino 5V and the ground pin is connected to the GND. The setup allows the Arduino to periodically read the temperature and the humidity using the DHT library. The room heater is represented by a heating lamp, electrically controlled using a 5V relay. The relay allows the Arduino to safely control a more powerful external load. The relay's control pin is connected to digital pin 53 on the Arduino. When pin 53 sets high, the relay activates and powers the heating lamp. When the pin is low, the relay deactivates and the heater turns off. The relay is powered with 5V and connected to the system's common ground. The fan is used for cooling when the temperature exceeds the set points. Since the Arduino cannot directly supply the current required by the fan, a transistor is used as a power interface. The transistor's control pin is connected to digital pin 31 on the Arduino. When pin 31 goes high, the transistor conducts and powers the fan. When the pin is low, the transistor blocks the current and the fan stops. The fan is powered by an external source, while its ground is shared with the Arduino ground. The temperature set point is adjusted by the user using potentiometer. The potentiometer has three terminals, one connected to 5V, one connected to ground, and the middle terminal connected to analog input A15 on the Arduino. The voltage measured on A15 varies according to the potentiometer's position. The Arduino then converts this value into a temperature set point ranging from 15 to 35 degrees Celsius. Two LEDs are used to indicate the system's stage. The red LED connected to pin 3 lights up when the heater or fan is active. The green LED connected to pin 2 lights up when the temperature is stable and matches the set points. Each LED is connected to the Arduino through a current limiting resistor. These LEDs provide a simple and quick way to visualize the system's operation. Here is the real operation of the system. We can observe the temperature displayed on the LCD screen, the activation of the heater or fan, and the response of the LEDs. The system automatically maintains the temperature around the set points.